Why we use simulants. To grow plants in space, we first have to understand one simple truth. Space is dirty. On Earth, soil is alive. It contains microbes, fungi, insects, organic matter, and nutrients that have been recycled for millions of years. On other worlds, however, we don't have soil as we know it. Instead, we have regolith. NASA defines regolith as dusty, crushed rock material created by meteorite impacts, radiation, and extreme temperature swings. Because we can't easily bring large amounts of real Moon or Mars soil back on Earth, our scientists rely on high-fidelity regolith simulants. These are carefully engineered materials designed to replicate the mineralogy, chemistry, grain size, and mechanical behavior of extraterrestrial surfaces. Using accurate simulants allows researchers to test systems safely, repeatedly, and realistically. Without them, we couldn't reliably predict how infrastructure, life support systems, or even future space gardens would behave on another planet. These simulants are the foundation that allows innovation to happen long before humans arrive. Types of simulant. Not all space dirt is the same. Each planetary body has a unique geological history, and that history shapes how regolith behaves. In our research and workshops, we focus on 3 primary categories of simulants. For the Moon, we simulate different regions such as the lunar highlands, the lunar mare, and the lunar South Pole. Each has a distinct composition. For example, lunar highland simulants like LHS-1 are rich in anorthosite and represent rugged, heavily catered terrain, while mare regions contain more basaltic material formed by ancient lava flows. These differences matter for both construction and agriculture. For Mars, simulant represents the general Martian surface as well as specific locations of interest, such as Jezero Crater, where ancient river deltas suggest Mars once had flowing water. Martian regolith contains iron oxides, sulfates, and perchlorates, chemicals that strongly influence plant growth and microbial activity. We also explore asteroid regolith, particularly carbon-rich materials similar to carbonaceous chondrites found on asteroids like Argyle. These materials are of interest because they may contain water-bearing minerals and organic compounds, making them potential resources for future space exploration and institute resource utilization. Testing for survival and infrastructure. Before planting a single seed, regolith simulants are used to tackle major survival challenges. One critical area is radiation protection. Researchers have tested Martian regolith simulants such as MGS-1 mixed with polymers or binders to evaluate whether the soil itself can shield astronauts from harmful cosmic radiation. These studies help determine whether habitats could be buried or built using local materials rather than relying solely on Earth-launched shielding. Another key challenge is water. On the Moon and asteroids, water is often trapped as ice or chemically bound within minerals. Scientists investigate thermal mining of volatiles by heating lunar regolith simulants to release water vapor and other gases. This process could provide drinking water, oxygen, and hydrogen fuel resources that are also essential for sustaining plant growth. Regolith is also studied from a geotechnical perspective. Using simulants like LHS-1, researchers measure strength, compaction, friction, and load-bearing capacity to understand how to build roads, landing pads, and habitats. These same properties affect plant roots, which must penetrate the material to anchor the plant and access water. How plants actually grow in regolith. When plants are finally introduced, regolith presents challenges unlike anything found in Earth soil. Extraterrestrial regolith contains no organic matter, no microbial ecosystem, and very limited bioavailable nutrients. Its particles are often sharp and angular, formed by impacts rather than erosion, which can lead damage roots and restrict growth. Despite these challenges, research has shown that plants can grow in regolith not without stress. In landmark experiments conducted by NASA, scientists grew the model plant Arabidopsis thaliana in actual Apollo-era lunar soil. The plants successfully germinated and completed their life cycle, but they exhibited slow growth, altered gene expression, and stress responses related to salt, metal toxicity, and oxidative damage. This demonstrated that while lunar regolith is not ideal, it is not completely incompatible with life. Similar experiments using lunar and Martian regolith simulants on Earth have shown that crops such as lettuce, radishes, tomatoes, and mustard greens can grow when nutrients are added. Without supplementation, growth is severely limited due to nitrogen and phosphorus deficiencies. Research also found that regolith compaction restricts oxygen flow to roots, requiring careful control of watering and structure. To overcome these issues, scientists experiment with regolith amendments such as compost, biochar, fertilizers, and beneficial microbes. Adding organic matter improves water retention and nutrient availability, transforming regolith from a hostile substrate into a functional growing medium. Hybrid systems combining regolith with hydroponics or raised bed designs are also being tested to reduce root stress. Fungi, microbes, and living soil energy. Plants are not the only organisms being studied. Fungi and microbes play a crucial role in preparing regolith for life. Certain fungi can chemically alter minerals, releasing nutrients through a process known as biomining. These organisms help make iron, phosphorus, and other elements more accessible to plants. Experiments with mycorrhizal fungi, which form symbiotic relationships with plant roots, have shown promise in regolith stimulants. These fungi extend the effective root system of plants, improving water and nutrient uptake while reducing stress. Other research focuses on using cyanobacteria and algae to slowly build organic matter, creating the first stages of a living soil system. This approach moves us away from simply planting in dirt and toward bioregenerative ecosystems, where plants, microbes, fungi, water, and atmosphere are all linked. These systems are essential for long-duration missions where resupply from Earth is impossible. From space dirt to space gardens. Growing plants in space is not just about food. Plants recycle carbon dioxide into oxygen, purify water, regulate humidity, and provide psychological comfort to astronauts living in extreme isolation. Every experiment with regolith simulants brings us closer to sustainable, self-sufficient habitats beyond Earth. By studying how plants and fungi interact with extraterrestrial soils, we are learning how to turn hostile environments into places where life can take root. In doing so, we are transforming space dirt into the foundation for future human survival, one garden at a time.